Welcome back to the Quantum Rings Quantum Summer School. Today, we're going to be talking about one of the hottest topics in quantum computing today, which is quantum error correction. Quantum error correction is essential in order to have fault-tolerant quantum computing. Our physical quantum hardware is noisy, so the basic idea is to take a bunch of physical qubits and encode them into logical qubits, which are robust to error. Let's get into it. So today we're learning about quantum error correction. We're going to start off talking about classical error correction, and then we're going to move on to talking about the simplest quantum error correction codes, which is the 3-qubit bit and phase flip repetition codes. Then we'll move on to the 9-qubit Shor code, which can correct any type of single qubit Pauli error. So that's errors that are either X, Y, or Z, or a linear combination of those. And then lastly, we'll talk about surface codes. So let's first talk about the concept of error correction. In general, the idea is that we have some physical bits, and these are prone to error, and we want to encode a bunch of physical bits into a logical bit that is protected against error. So if something happens to one or more than one of the physical bits, you can detect that an error has occurred and correct back to the logical subspace. So the simplest example is a repetition code. So for instance, if your physical bits, you had 3 of them, then you want to turn this into some logical interpretation. So we can say that if the majority of the bits are 0, then we interpret that as a logical 0. And if the majority of bits are 1, we interpret that as a logical 1. So here, this would be 0, 0, 0, 0, 1, 1, 1, 1. And then here, these top 2 cases are the error-free cases, because the all 1 state and the all 0 state are our logical 0 and logical 1. But these other ones are off from the logical state by 1 bit, so we can detect and correct for that error. So I just want to emphasize here that if we have 1 bit flipped, then we can detect and correct that error. If we had 2 bits flipped, for instance, if we started in logical 0, and then we had some errors, and we ended up in this state, we would incorrectly assume that this was a logical 1. So this would lead to a logical error. And the hope is that the logical error rate is much lower than the physical error rate. So another question you could ask is, what if we had 4 bits encoded into 1 logical bit? Well, again, our logical states are going to be the all 0 state. And oftentimes we'll denote with like a bar on top the logical state. So all of these states, which are either fully 0 or only 1 off from 0, these are all going to be interpreted as 0. And then these states, which are all 1s or only contain 1 0, are going to be interpreted as 1. But then all of these errors here have 2 0s and 2 1s. So we have no idea which of the logical states is supposed to be, or what it started from. So here we can detect the error, but not correct it. So generally speaking, we can draw this picture here, where we have our logical code space with our 0 and 1 state, and then around that is the set of correctable errors. So if we move to one of those errors, we can correct back into our logical subspace. And then there's even bigger circle around, which contains everything which is detectable errors, and some of which are not correctable. And a lot of times when we're talking about error correction codes, this is the notation that we use, NKD code. So N would be the number of physical bits or qubits, K is the number of logical bits or qubits, and D is the code distance. So by code distance, we mean how what is the minimum number of errors to get from one logical code word to another logical code word. So in this case, with just logical 0 and logical 1, what's the number of errors that it takes, minimum number of errors, to get from logical 0 to logical 1? And we can correct d minus 1 over 2 errors, where that notation is just rounding down to the nearest integer. And this makes sense because if we have too many errors, like more than d over 2 errors, then we'll end up closer to the wrong logical result. So now moving on to quantum error correction. We can't just do a simple repetition code like we did with a classical bit. We can't say, okay, I have my state psi, and then I'm just gonna map it to psi, psi, psi. And the reason that we can't do this is because of the no cloning theorem. You can't take an arbitrary quantum state and copy it onto another qubit. This is not allowed. So we need to come up with some other idea. And the idea is to spread the quantum information of the state psi across many qubits in a highly entangled state. Okay, so here's a very limited example of a quantum error correction code, which is the 3-qubit bit flip repetition code. And the reason that it's limited is because we want to correct for bit flips, right? But that's not the only type of error that can occur for a qubit. So ideally, we would want to be able to detect and correct any type of error. But this is a very simple example that can help us understand the underlying mechanism behind a lot of quantum error correction codes. So we're going to define our logical 0 state as all qubits being 0, and our logical 1 state as all qubits being 1. We're going to start off with some qubit, and here in purple I've just labeled the index numbers. So qubit 0 is going to be in the state psi, and that's what we want our logical state to be. So the first thing that we're going to do is we're going to encode our state psi into our logical state. So we know that if psi is alpha 0 plus beta 1, then we want to map this to alpha 0, 0, 0 plus beta 1, 1, 1. And we can do this using C0 gates. So here, if we start off with psi, then here, after the first C0, the second qubit is going to have the same value as psi for each term. So at this point, we'd be in the state alpha 0, 0, 0 plus beta 1, 1, 0, because the third qubit is not on the same page yet. And then here, we would end up with that logical state that we want. The next step is that we would have some quantum circuit and potentially some errors in that quantum circuit. And here's where we would apply our logical operations. So it's important to note that when we're doing a quantum error correction scheme, we want to apply gates to the logical states. This is not going to look the same as applying a Hadamard gate to a logical qubit is not going to be the same as applying a Hadamard gate to a physical qubit. The next part of the circuit is getting the error syndrome. Basically, we want to figure out what error occurred so then we can correct for it. And to do this, we're going to use 2 ancilla or helper qubits, which are going to start off in the 0 state. And we're going to check the parity of pairs of qubits. What do I mean by parity? I mean if they're in the same state or different states. So we're doing that with 2 C0 gates. So for instance, these 2 C0 gates here will tell us if qubits 0 and 1 are in the same state or different states. So if they're in the same state, we'll get either 0 or 2 X gates applied to our ancilla qubit. So it's going to be in the 0 state. And if they're different from each other, only 1 will get applied and will be in the 1 state. So this is a way to check the parity of 2 qubits. We'll check the parity of qubits 0 and 1 here, and the parity of qubits 1 and 2 here. And we'll get some error syndrome, which is either 0, 0, 0, 1, 1, 0, or 1, 1. And then based on the error syndrome, we're going to correct our states. And then at the end here, we should be back in that state alpha 0, 0, 0 plus beta 1, 1, 1. Again, only if the error that occurred in the part with the quantum circuit and errors is a single qubit bit flip error. So let's talk about the error syndromes briefly. So first, let's think about what the states will be right before getting the error syndrome. So if we had no bit flips, we'd be doing fine. If the 0th qubit had a bit flip, then we would get this. We can just fill out the rest of this here. Then we can think about what our syndrome measurement would be. So here, the parity of qubits 0 and 1 and 1 and 2 is both even. So these will both be 0. And here, the parity of qubits 0 and 1 is odd, and 1 and 2 is even. Here, they're both odd, and here, only 1 and 2 is odd. So now we can think about the correction that we would need to apply. So for the first case, we're already in the right state, so we can just apply the identity to everything and we'll be good. For the second one, we know that we need to apply an X gate on the 0th qubit. Here we need an X gate on the second qubit, and finally an X gate on the second qubit. So now we're going to move over to the coding notebook, where we're going to briefly talk about this code again, and then we're going to talk about turning this into a phase flip code, and then also talk about the 9-qubit Shor code. Okay, so first, let's import all the libraries that we need and get our helper functions as well. So this here is kind of repeating a lot that I just talked about, but it's there if you wanna look at it again more closely. So let's just code up our single qubit bit flip repetition code. So the first thing we want to do optionally is prepare our state. So here's where we would prepare our qubit 0 into the state that we want. The next step is encoding, so we know that we want to copy over the state from qubit 0 to qubit 1. I say copy, but I don't mean literally making a clone. I mean extending it to include more qubits, basically. We're creating this highly entangled state. And then also with qubit 2. Then here is where we're going to have our logical gates or whatever noise that we're going to have. And then we want to do the detection. So we need our 4 CNOT gates to check the parity. So first we're going to check the parity of qubits 0 and 1. So we'll use our ancilla qubit, which is going to be indices 3 and 4. First, we're going to measure our ancilla qubits to get the error syndrome. And then we're going to measure our other qubits. And then we're going to do some post-processing in order to perform the bit flip that we need. So here's our circuit where we have our encoding, we have our parity checks, syndrome measurement, and then finally measuring the 3 qubits. So we can run our circuit 1,000 times, and then for each of those we can go through, get the error syndrome, get the data string, so the state of the first 3 qubits, and then apply the correction rule that we need. So if the syndrome is 0, 0, then it's just going to be our data string, no correction needed. Whereas if the syndrome is 1, 0, then we know from before that we want to flip our data string at the 0th index. It's just a helper function from above, flipping a bit at a certain index in a data string. Here would be the first one, and then the last one would be the second one. And then we're gonna get those, we're gonna update the corrected counts. So we're just gonna add it to what was there before and plot the histogram. So here we can see that we measured 0, 0, 0 every time, given that we post-process for our error syndrome. So now we can add in some noise, for instance. So let me add a bit flip on, let's say, qubit 0. And we still get 0, 0, 0 every time because this code can correct for single qubit bit flip errors. Again, it doesn't matter which qubit gets the error on it. But if we had 2 of them with an error, this is going to lead to a logical error. This code cannot correct a phase flip error. The reason that we can't detect a phase flip error is that if a phase flip error occurs, that does not change the parity of neighboring qubits. So our error syndrome would not tell us anything about whether or not there was a phase flip, and therefore we can't correct for it. So here's a question to think about if you're interested. It's kind of like a paradox that's not really a paradox. We can also make a more compact version of the quantum error correction code by absorbing the parity measurements and correction into a pair of CNOTs and a Toffoli gate, which remember is a double controlled X gate. And then in the end, the logical state will just be on qubit 0. So here we would just have, or let me draw the circuit as it is. We have our encoding. Here is where we have the detecting and correcting. So we have 2 CNOTs and a Toffoli gate. And this works exactly the same way, except now we're only measuring Q0, and Q0 stores the logical state. So again, we can have bit flips, and it doesn't make any difference. But if we had 2 qubits bit flipped, we would have a logical error. So here are some challenge problems to think about. So what are the weaknesses of the quantum error correction code that we just did? And think about what you would want a quantum error correction code to do to actually be useful. And then what would you change in the circuit above so that the logical state is protected against a 1 qubit phase flip rather than bit flip? I would encourage you to pause the video and think about this before you continue on, because we're going to cover that next. Yeah, so some of the weaknesses of the code, it can only correct 1 type of error, and it also can't correct many errors. So the distance of the code is not very large. So we want a code with a larger distance, and we want to be able to correct different types of errors as well. So if we want to change the circuit to protect against phase flips instead of bit flips, all we need to do is change basis. So right before and right after the part where we have the quantum circuit / errors, we're gonna put Hadamard gates. And this will rotate us into the X basis. So here I just written down some functions which do what we want. So this is the encoding section. And the flip type can either be bit or phase. We'll have our 3 qubits. We have our CX gates. But then if we're doing a phase flip code, then we should apply a Hadamard to all the qubits in the register. And then here, same exact thing, where we have our 2 controlled knots and a Toffoli. But if we're doing a phase flip code, then we should apply Hadamards to everything right beforehand. So Here we can do the whole circuit together, but now in the part where we would normally apply a logical operation or some errors would occur, we can just put some identity gates and then use Qiskit's error simulator to have a noisy backend and have Pauli errors on during the identity gates. So here, for instance, we can set the probability of a bit flip occurring. This is how we define a bit flip error. It's a Pauli error which has a p probability of having a x gate and a 1 minus p probability of applying the identity gate. We make a noise model with this bit flip error. We make our simulator backend with the noise model. And then we need to transpile our quantum circuit. And here we make sure that the optimization level is 0, otherwise it gets rid of all identity gates. And now we can run it and get our counts. So if the probability was 0, then we should have no errors, so we remain in the logical 0 state. But if we had, for instance, a 5% error, now we're going to have some logical errors, because there will be some times when more than one qubit is going to experience a bit flip error. But let's think about the physical versus logical error rate. We said 5%. So 5% of 1,000 is 50. So we'd expect around 50 errors if we're just using one qubit. But now with this repetition code, we've greatly reduced the effective error rate. Another thing you can do is you can also prepare the qubit in some other state. So preparing the one state instead, then things would just flip around. So now let's talk about the phase flip code. So here's the same thing, but now we're doing phase flip code. So we have these Hadamard gates sandwiching where our error would occur. And then here we can have a Pauli Z error. And again, here if the error rate is, physical error rate is 10%, then our logical error rate is much lower because we would expect around 100 errors from just the physical error rate. So some questions to think about is, why can't we detect X errors with the phase flip code or Z errors with the bit flip code? We talked about the first one a little bit earlier. And can you think of any way to combine them to get the best of both worlds? And that's the Shor code that we're going to talk about. So maybe pause the video and think about how you could combine these two codes. I'll give you a hint, it should use 9 qubits. And then I also want you to think about Y errors. Can you detect and correct Y errors with bit flip or phase flip code? And why or why not? So now let's talk about the Shor code. So the Shor code combines the bit flip and phase flip codes together to be able to correct any single qubit Pauli error. So Pauli error is a linear combination of sigma x, sigma y, sigma z, and the identity. So the Shor code encodes the following logical states. For the logical 0 state, we want 0, 0, 0 plus 1, 1, 1. Well, we can create the state 0 plus 1 by applying a Hadamard gate to qubit 0, and then we can use the controlled NOT gate to copy that down onto the other qubits. And then for the logical 1 state, we can prepare the state 1 and apply a Hadamard gate to get the minus state 0, minus 1, and then use 2 C0 gates to copy that down onto the other 2 qubits. So basically, the first part of the circuit, the encoding part, is just going to be a Hadamard and 2 C0s, and there's going to be 3 copies of that on our 3 clusters of qubits. So the way that we're going to realize this encoding of logical states is we're going to have 3 bit flip repetition codes sandwiched between 1 phase flip repetition code. So we're going to split into 3 blocks of 3 qubits, and then around that entire thing, we're going to have 1 big phase flip code on the first qubit in each block. So we get our logical state with any bit flip error corrected, and then if there was a phase flip error that occurred within that, it would also be mapped onto that logical state, and then we could correct that phase flip error with our phase flip code. So the first thing we want to do is encode the phase flip. And we want to apply this on qubits 0, 3, and 6. So those are the first qubits in each block in place so that it overwrites the current quantum circuit. And then for each of the blocks, we want to do a bit flip repetition code. So we need to encode Then we're going to have some noise. So here I'm using the identity gates again, which we're going to use with the error simulator. And then here we want to correct the bit flip errors. And then finally, we want to correct the phase errors. Okay, so let's see what this circuit looks like. So you can see in the middle here, there's a bit flip repetition code, and there's 3 copies of them stacked on top of each other. And then on the outside, if you look at just qubits 0, 3, and 6, we have that phase flip repetition code. And at the end, we're just measuring Q0. So we can look at what happens. In this case, I'm adding both a bit flip error and a phase flip error with some probability of a bit flip and probability of a phase flip. If it's 0, then we incur no logical error. But if we have for maybe 5% error on each, then we're going to incur some logical errors. So here this is just the shortcode as a function, running the shortcode with noise with some bit flip and phase flip probability. And here I'm just we're checking the error rate. So we want to measure logical 0 at the end, so we're checking what % of the time we measured 1. You can modify this if you want to make some other initial state that you're supposed to end up with. So for instance, you could prep the plus state by applying a Hadamard gate at the start of the shortcode here, and then apply a Hadamard gate right before measurement. And then you could also check the error rate that way on the plus state. So one thing that we can think about is sweeping over the phase flip errors and looking at that rate of error. I'm just keeping the bit flip error 0 here. Okay, so now we can see what the logical error rate is compared to the physical error rate. And we can see that for up until about like 5%, the logical error rate is lower than the physical error rate. This is good. This means that we're getting some advantage from using our quantum error correction code. But at some point it crosses over and the logical error rate is actually higher than the physical error rate. This is really bad because that means our quantum error correction code is actually making things worse. So the main goal of quantum error correction is to make it such that the logical error rate is a huge advantage over the physical error rate. And then in addition to that, get the physical error rate as low as possible. So we're kind of tackling this from both angles in the field right now. Both people trying to make the physical error rate as low as possible and make the logical error rate as big of an advantage as they can over the physical error rate. So here's some more things to think about if you're interested. But I'm going to hop back over to my iPad just to talk about another type of quantum error correction code, which is really hot in the field, which is the surface code. The idea behind the surface code is to take an array of qubits laid out in a 2D grid and encode that into one logical qubit. So I'm going to talk about the 913 surface code. So 9 physical qubits is 1 logical qubit with a code distance of 3. That means we can detect and correct 1 error. So here we have 9 data qubits, which we're showing in blue, and 8 ancilla qubits, which we're showing in orange. We can basically block this out on a grid. So connect all of the data qubits with a line and then shade in the regions in between. And then each of these regions has 1 ancilla qubit in it. So for instance, here we have this purple square, which has an ancilla in it. And all the purple squares are going to be Z stabilizers, and all the yellow squares are going to be X stabilizers. And the idea is that we're going to use parity checks to detect errors. And those errors are going to give us a really good idea of where the error occurred. So we're going to be able to pinpoint which qubit had the error, and that makes it easy to correct. So for Z stabilizer, we want to check the parity of our 4 qubits in the little square around our ancilla. So we know that for 2 qubits, we just did 2 C0 gates. Same thing here, we can just do 4 C0 gates. So then if an even number of the qubits are 1, we're going to have even parity, and if an odd number of the qubits are 1, we're going to have odd parity. So we can think about the results of our stabilizer measurements. So if all of them are 0, then we have no C0 gates, and this is 0. Here we would have 1. Here we would have 1. Here it's even again, 0. And I'm just going to fill this out quickly. But it follows the same pattern. So if we have even parity, we're going to measure 0. And if we have odd parity, we're going to measure 1. Then we're also going to have our X stabilizers. And the X stabilizer is going to tell us about the phase parity of the qubits, essentially. So here the circuit for the syndrome measurement looks a little bit different. So our ancilla is going to start in the 0 state and then get a Hadamard applied to it, so it's in the plus state. And then recall from many episodes ago, we talked about phase kickback. So actually, when we apply a C0 gate, it doesn't just affect the target qubit. You can also have phase kicked back onto the control qubit. So that's what's happening here. So basically, if qubit 0 is in the plus state, then a phase of +1 is going to be kicked back onto the control qubit. And if qubit 0 was in the minus state, then a phase of -1 would be kicked back. So basically, we know that if a phase of +1 is kicked back onto the plus state, it will stay in plus. If a phase of -1 is kicked back, it will turn into the minus state. So basically, at the end of here, we're either going to be in plus or minus state. We apply a Hadamard that sends us to 0 or 1. So if the phase parity was even, we'll measure 0, and if the phase parity was odd, we'd measure 1. So here, if the phase parity would be odd, and here the phase parity would be even. Okay, so that's our stabilizers. Now we can talk about how we detect and correct errors. So here's our stabilizer, for instance, which is Z4, Z5, Z7, Z8, these 4 qubits around it. And an example of an error would be a bit flip on qubit 5. So this would be a poly X on qubit 5. Poly X at qubit 5 does not commute with poly Z at qubit 5. It commutes with anything on any other qubit, but not qubit 5. So in this case, when we normally start out with an even parity, we're going to get an odd parity on that plaquette because qubit 5 is flipped compared to all of the other ones. And so that's definitely going to give us a 1, which is going to flag that there's an error. If there's a phase flip on qubit 7, for instance, the phase flip commutes with our stabilizer. And another way you can think about it is a phase flip does not change the parity of our 4 qubit plaquette. So we can't detect the phase flip error. But the opposite of everything I've just said is true for the X stabilizer. So for the X stabilizer, we cannot detect an X error, but we can detect a Z error. So we could look at some example error syndromes. So here we have a 1 on the ancillas associated with these two plaquettes. And so since it's an X stabilizer that's getting flagged, we know that there's a Z error that occurred. So we can tell that there's a Z error on qubit 1. So all we need to do is just apply a Z gate to qubit 1 in order to fix this. Here's another example. So here we definitely have some X error and some Z error. And we can see that it looks like an X error on qubit 4 and a Z error on qubit 7. But one thing I want to point out here is that different types of errors can lead to the same error syndrome. So it could also be the case that we have Z7 as an error, but X0 and X8. So the surface code is not super useful. It's kind of like the 3-qubit bit flip repetition code. It's not giving us much of an advantage because a lot of errors look the same. We can still only detect and correct one error accurately. But if we have a larger surface code, then we can have a larger code distance. So for example, Google has done a bunch of experiments with surface codes, and they've done this 913 code. If you do 25 physical qubits, you can get one logical qubit with code distance of 5. So that means you can detect and correct 2 errors. And then if you had 49 qubits, you could detect and correct 3 errors. I would just briefly mention what the logical operations would be here. So a logical X would be X gates applied across one row in the array, and a Z gate would be Z gates applied along one column in the array. And maybe just to note that logical X and logical Z are not going to commute with each other because there's an X and a Z on one of the qubits, and those don't commute with each other. So in general, logical operations need to behave exactly the same on logical qubits as physical gates applied to physical qubits. Today, we got a small introduction into the field of quantum error correction. We learned how we can take a bunch of physical qubits, which are prone to noise and error, and encode them into logical qubits, which are robust to local noise and error. Next week is going to be the last episode of the series, and we're going to do a capstone where we do quantum approximate optimization algorithm with 100 qubits. I'll see you then.